Section 2.2, describing sets. We started last time with a little bit of vocabulary. We referenced what a set was and what an element is. And we talked about different ways of describing sets. We looked a little bit of notation, some different common mathematical notations. And we looked at how to write different pieces of information in such a way that we talked about equal sets, equivalent sets. And we left off with complement, I believe. Null set, yes, complement is our last idea. Complement being the same, in the same universal set, but it's the exact opposite of the set we're working in. So we had that example. So we're going to take a look at another idea of sets. So if we have a set, another idea within a set would be a subset. So it's a smaller collection inside of a bigger collection. So visually, let me draw you what that would look like in terms of a Venn diagram. You've got this rectangle, that's my universal set U, and you've got set A, and inside of it is set B. Okay, so we'll see how tiny I can write. Here is set B, here is set A, B is inside of it, and here's my universal set U. So B is a smaller collection of the same stuff that A was. So here would be an example, just a verbal example of this. So let's say, for instance, you were talking about your family. Okay, so I know when I say family, that can mean lots of things. Family might be the people who live in my house family, right? Sometimes that's called a nuclear family. Or family might be something much more broad, like the people I was just with on Labor Day. Or it might simply include my brothers and sisters and their family, my parents, or something like that. This is sort of a broader definition of family. So if we talk in that kind of a sense, this capital A would be this broad definition of family. And then the set B inside of there would be maybe my smaller family, the people I live with in my own house. Okay? It's just a smaller collection of the same idea. Now, this is where it gets a little bit kind of confusing, and it's not meant to be. But the reality is that the way that subset is written, you could have sets A and B that are exactly the same. Like I could say family, and the only family that I have is the family that lives in my house. So both A and B, when I say family, they would mean the same thing. And by definition, because everything in one set is inside of the other one, one is a subset of the other. It feels weird because they're really just equal. Why would I call them a subset? Well, in order to avoid that language, we have something also called a proper subset. So a proper subset is a subset B inside of A. So it has to be a subset first, where there's at least one element in A that is not in B. So imagine that I have my circles. Set B is my 5 people plus me that live in my house, so that's my set B. And then set A includes just at least one more person, my mom. Okay? So the family, when I say family, perhaps what I'm saying is the people who live in my house plus my mom. Or I can just talk about the people who live in my house. But the smaller circle really is smaller, legit smaller than the bigger circle. Because subset does not include that possibility. Right? It means that it doesn't have to actually be bigger than the outer set. Let me give you a little bit of notation. The notation for subset looks like this. It kind of looks like a union symbol, right? Like a U turned on its side. Sometimes people look at it and think it looks like a C. It's a little bit more squished than a C, but you could say it looks like a C, right? Sometimes people look at it and it actually, and this is a better notational and sort of a visualization, think about it somehow as A being less than or equal to B. And that's actually a really good description because it has this line on the bottom, right? And when we put that line on the bottom of less than or equal to, it means that the first thing could actually equal the second one, right? Well, you can think about it that way as well with this notation right here. This little line means they really could be the same. It could be a subset that is equal to the one that it already was, the other one on the other side. I'm sorry, I totally wrote that backwards too. I'm not keeping in mind what I wrote down before. This was actually, B was a subset of A, the way that I had described it above. B is a subset of A. So let's actually make it match. I'm sorry. Please, please, please fix your notes. Okay, B is contained in A. Proper subset has the notation that looks very similar. What do you think it might be different in? It doesn't have the line underneath it. You're exactly right. And if you think back to the notation where you actually have the less than kind of sign, something like this, that's what that means. It really is smaller, right? It's not smaller or equal to, like it's smaller. It is really less than. And you have the same sort of feeling of that with the B contained, this B, right? B is a subset of A. This is a proper containment. It really is smaller. It can't be the same thing. There is something in the set A that is not in set B because B is smaller than A. Please don't sort of gloss over the fact that this piece right in here is here. It isn't just smaller. It's also contained inside of it. It really is a subset. Okay, so I can't have just something smaller than it was before. It has to be both smaller and be contained inside the one. And you'll hear the language when I say it. Sometimes I'll say something like this. B is contained inside of A. That's the same language as B is a subset of A. It has this sort of idea of being somehow inside of something else. Okay? All right, so when we're talking about subsets, the question you might want to know is like how many subsets are there? And you'd be surprised how small the set can be and have a number of subsets. So if you have a set that has n elements, then there are 2 to the n subsets and 2 to the n minus 1 proper subsets. And we're just going to use this mathematical formula first, and then I'm just going to do a really simple case for you so you can see it. I'm not going to do it with 5 elements, that's part A over here, because it becomes cumbersome very quickly, but I'll do it with a few elements after I show you this example, okay? So let's do the example with the notation first, these formulas. It says, consider the set of all mathematics faculty at OBU, and just in case you didn't know, there's 5 of us. Okay, we have 5 mathematics faculty. And we're wanting to do something like create a committee that says, you know, like goes out and visits students in their dorm rooms. I don't know, we're going to create a committee and does something, okay? We want to know how many different committees, how many different groupings we could create. Well, we could create different groupings based on how many subsets there are. So, how do we do this? Well, it says that I will have 2 raised to the n power, and n is the number of elements in my set. So how many elements are there in my set? 5, because there's 5 faculty members. Do you know what 2 to the 5th is? 32. It's 32. 2 to the 3rd is 8, and 2 to the 5th is 32. So there are 32 subsets. That's why I'm not going to do this example. I don't want to write out 32 subsets. Okay? There are 32 subsets when you have just 5 people. And then part B says how many different proper subsets are there? What is the only difference in the formula between the subsets and the proper subsets? It's minus 1. So if I know how many subsets there are, how many proper subsets would I get? 1 less. And in this case, I would get 31. Everybody with me so far? Okay, let me do an example. This isn't actually written in here, but I'm going to do one here that has 3 elements. And I mentioned just a moment ago, somebody had given the possibility that 2 to the 5th might be 8. And I said, it's not quite. 2 to the 3rd actually is 8. So I should be getting 8 subsets, right? That's the answer I should get for the number of subsets. So I'm going to do 3 elements, and I'm going to do just the letters A, B, C. Okay, everybody good so far? A, B, and C. All right, so one possibility for a subset is that it's a set that has everybody in it. Okay, it's not a proper subset, right? But that's a subset. It's the awkward, weird one that equals the one we already have, but it is one. If I don't have all 3 people in my subset, how many people could I have? 2. I could have 2. So let's write down all of my possible 2 subsets. So I could have A and B. What else could I have? A and C. So this is the subset number 3. Or I could have what? B and C. Are those all of my 2-person or 2-element subsets? I think so. But if I don't have 3 and I don't have 2, how many else numbers of people could I have in my set? I could have 1. Again, it feels a little bit awkward, but it still works with the definition. The definition simply says it's a smaller collection of the same stuff we already have. So I could have a set with A only in it, B only in it, or C only in it? If I don't have a set that has 3 elements in it, or 2 elements in it, or 1 element in it, how many elements in there could there be? 0. Okay? The last option is I could be talking about the empty set. That's a subset of people. This is the problem that we're running into right now in the math department. We're trying to find a time when we can all meet to do something. And every time somebody suggests something, somebody else can't do it then. We can't seem to have this mutually agreed upon time when we're all available. We're running into these problems. So right now we've got an empty set of time spots is what we've got of when we're all available. All right, so do you see 8 of them? Yeah, and I'm not going to ask you to write out the number of subsets, but this is where this is coming from. So if I were to do this, I could do it for 5 elements as well. I do all of the groups that have 5 in it, that'd be 1. All the groups that have 4 in it, all that have 3, all that have 2, all that have 1, and I'd also have the empty set. And then if you're looking down here and you're trying to decide, okay, which one gets eliminated when I'm talking about the proper subsets, which one does get eliminated when I refer to the proper subsets of ABC? The one with all of them in it. This is not proper. All the rest of them are proper. Remember, proper means it really is a subset, and all these were, and it's smaller. And ABC is not smaller. So it gets eliminated when we talk about being proper. Okay, let's take another example along with these numbers of subsets. Suppose you have a set about which you know that there are 63 proper subsets. How many elements would be in the set? Okay, so what do you know about proper subsets? There is a relationship on a previous slide that we know. What is it? It's 1 less than what? 2 to the n. Very good. Okay, so it's 1 less than 2 to the n. This is how many proper subsets something has. And we are being told in this problem that this value equals 63. Okay, that's what we're being told so far. It's a little bit of solving equations. It's not anything terribly difficult, but the first thing that we would recognize is that if I actually added the 1 to both sides, I would have this as 2 to the n equals to 64. And then from here, you can actually play with your calculator to figure out what this would be. Take 2 and put in a power, 2 to the 5th, 2 to the 8th, 2 to the 22nd. I don't care what you choose. But what you're looking for is you're looking for the one that gives you the result of 64. And what value does give you the result of 64? 6. 6 actually makes this work. So the n being 6 means that I have 6 elements in my set. And with a 6-element set, I will have 64 subsets or 63 proper subsets. So this one just works the problem backwards. All right, the next thing we're going to do, and these 2 next problems look very much the same, but the directions are slightly different on the problems. This directions say that we're going to use either the element of or not an element of symbol in each one of the blanks. We're going to put one of those 2 symbols in each blank to make the statement true or false. Okay, so that's what we're looking at. All right, so on the very first one, this one on the left-hand side, what does that symbol mean on the left-hand side of A? The null set, or we also called it an empty set, right? Okay, and what is that thing on the right? It's a set with 0 in it, right? So on the right-hand side we have a set, and on the left-hand side we have a empty set. So what's going to go between these? Is it an element of, or is it not an element of? It is not an element of. Do you know why?
Because there's an element with 0. 0 is an element.
Okay, that's actually a good argument. So is there an element in the set on the right? Yeah, it's element 0, right? 0 is in the right-hand side, correct? So if we wanted to have something on the left-hand side that would make this an element symbol, it'd have to be the number 0, because there's only one thing in it. Another thing to think about as you're arguing or thinking about this statement, the empty set is a set. Are you with me? It's not an element at all. It's a set. In fact, take a look at part C. What looks distinctly different about the way C begins than the way B or D begins? Visually, what's different? The brackets, right? There are brackets around this. The very fact that there are brackets around that means what? It's a set. Are you guys with me? This one on part C is a set on the left and it's a set on the right. And the right-hand set's not terribly complicated. It looks funny, right? 1 plus 2 and 1 plus 3 and so forth. It looks funny. But it's just a set on both sides. Okay? So I know I skipped B. I'll go back to it. But on part C, this is a set on the left. And the symbols I'm using right now are element symbols, right? This curly brace 4 isn't an element. It's a set. So right here in this blank right here, I have to use the not element symbol. Not because there's not a 4 over here. There in fact is. 1 plus 3 is 4. That's not the problem. The problem is that it's this value on the left with the curly braces isn't an element at all. It's a set. So I can't talk about a set being an element of what's on the right-hand side. Okay, let's go back up to part B. Part B looks a little bit awkward on the right-hand side because it's set builder notation, right? We encountered this before, this set notation. So sometimes it's helpful if you use the set notation to try and figure out what it's actually referring to. This says x such that x equals 2n. N is an element of the natural numbers. So what does this piece mean?
1, 2, 3, 4.
Good. Natural numbers. We saw that one last time or a couple times ago. We've got 1, 2, 3, 4, 5, 6, and so on. That's the natural numbers. So what this is saying is I can take those natural numbers and I can plug them into the n value here. So I can plug in the number 1 and I can plug in the number 2 and I can plug in the number 3. And if I do that, what set am I getting? Even numbers. This is 1, 2, 3, ... If I plug in 1, I get 1 times 2 is 2. If I plug in 2, I get 2 times 2 is 4. If I plug in 3, I get 3 times 2 is 6. If I plug in 4, I get 4 times 2 is 8. And I keep going. Is everybody with me on that? This notation at the end tells you. N being a natural number tells you that n is the counting numbers 1, 2, 3, 4, 5, and so on. The first part tells you what has to be true about that counting number. You have to multiply it by 2, and then you get this list of numbers. In this case, it's the even numbers. Everybody good? Yes, Kaylee?
You can't use decimals as a natural number?
No, natural numbers are not decimals. Those would be considered rational numbers. So if it said rational numbers, yes, this would be a much more broad description, wouldn't it? But this one actually specifically eliminated that possibility by telling us it's natural numbers. All right, so the question ends up being, let me first make notice with you. 15 and 16, those would be elements because they don't have the curly braces. So we could actually decide something now, okay? Is 15 an element of that list of numbers that I just wrote down? No. Why not? It's not even. It's an odd number. So this value right here is not an element of, but for a very different reason, right? It's not the same reason as part C. Part C was not an element because we had this weird set thing going on. Part B is not an element because it's an odd versus even issue. How about D? This one's the simplest one. We should have started here. I'll have to remember that next time. D, 16. Is it an element or is it not an element of the set of numbers 2, 4, 6, 8, 10, ... Yes. In fact, it's kind of funny that last one is actually the same list of numbers that I got, wasn't it? From above, yeah. And 16 actually is in that list. Okay, so this is element stuff. Element of, not an element of. What is different on question 8?
Is it subset?
Yeah. This notation means subset or not a subset. So I want you to take a look at A and C, D and B. The only way it can be a subset is if it's a set itself, right? So on the left-hand side, part A, is that a set?
Yeah.
Yes, that is the null set, correct? On part B, is that a set? No. So on part B, already it fails. It fails to be a subset because it's not even a set. It doesn't even make sense to talk about it that way. Part C, is that a set? Yes. It's not a very exciting set. It's only got one member in it, but it's a set. And how do I know? Curly braces, right? The curly braces tell me. What about letter D? Not a set because it's not in curly braces, right? So D I can fill in not a subset. The not a subsets are easier to do. Now we have to go back to part A and part C and decide. We know we have sets, but are they the actually proper subset? I mean, are they actually subsets of the one on the right? All right, so let's talk about the first one. Empty set. Is the empty set a subset of the set that contains the number 0? I'm getting some shaking heads, some blank stares. Let's go back to the definition first, and then I'll go back to an example I did. Oops, went one too far. The definition says B is a subset of A if, I should say, and only if every element of B is an element of A. Is every element of the empty set also an element of the set containing the number 0? It's a really weird way of saying it, isn't it? Because there's nothing in the empty set. But by default, it works. Every element in the empty set, of which there's nothing, is an element of anything, actually. It's an element of every set, right? So the empty set is a subset of any set. And I did an example. I know I'm going to come back to this slide just a second. Right down here, do you remember my example? All the elements with 3, all the sets that had 2, all the sets that had 1, and then we had the very unexciting empty set at the very end. By default, that is a subset. All right, let's look at C then. C has the set with the element 4 in it on the left. Amanda?
If those were reversed, it wouldn't work. Okay.
Correct.
Okay.
If they were reversed, if it said this,
Yeah.
that would be not a proper set, or not a subset. It would be not a proper subset too, but it would be not a subset, correct? Because the set on the left has the number 0 in it,
Yeah.
and the set on the right has nothing in it. It's exactly right. Number 4, letter C with the 4 inside the curly braces. It could be a subset because it's a set anyway. So the other condition has to be, is everything in this set, which is exactly one number 4. In other words, is the 4 in this set? And this is an awkward looking set, but could I write it in a different way that would look a little bit friendlier? Sure. What is the set that's on the right-hand side for real? 3, 4, 5, and 6. So don't be afraid to simplify the way that a set is given to you. You can do that. Is the element 4 in the set that's on the right? Yes, it is. Which means that the subset containing only 4, the set containing only 4 is a subset of the set containing 3, 4, 5, and 6. Now, it is true you could also write both on part A and on part C. This wasn't asked for here, but you could use the symbol like this in here as well. These are proper subsets as well. Proper just means they have fewer elements on the left than they do on the right. There's less in them, right? And there are. There's nothing in the first one on the left, and on C there's only one thing on the left, and there's 4 things on the right. So we can talk about it that way too. All right, I had mentioned last time we actually used an example of the fundamental counting principle, and I said, I know that's coming up soon, and I didn't realize even when I said it how soon, but it's actually in the same lesson. The fundamental counting principle says the following. If an event M can occur in little m ways, an event capital N can occur in, that's a typo, little n ways. Write little n right here for me. Then event M, capital, followed by event N, capital, can occur in M times N ways. And this is just talking about making an argument of different ways things can happen. A really good example of this is when you go to Subway, and if they had a restriction that says you can get 1 meat and there's 6 meats, and you can get 1 cheese and there's 10 cheeses, and you can get 1 vegetable and there's 15 vegetables, then you just multiply the number of things you have options of together. Now the example that I've got in Sonic drinks, same way. You know how they tell you how many millions of combinations you can make out of their drinks? They're doing an argument similar to this. Now, the argument I have here is a little different one, but it's the same idea. How many different outfits can be created from 3 shirts, 4 skirts, and 5 pairs of shoes? And of course, the assumption is everything matches, or you don't care. I don't know. I don't think it matters anymore to match. My teenagers don't match all the time, and they think it's cool. Do you got care? It doesn't matter. Oh, then this is fabulous. This works just perfectly then. All right, so what this is saying then is what am I going to do with the 3, 4, and 5? I'm going to multiply them. I have 3 shirts, I have 4 skirts, and then I have 5 pair of shoes. So I can multiply 3 times 4 times 5, and what will I get? That's right, it is 60. So there are 60 outfits that I can create with those particular pieces of clothing. You had no idea that there were so many outfits in your closet, but now you do, right? Absolutely. All right, here's another example of this fundamental counting principle. You have 6 favorite stores in the mall. In how many ways can the following happen? You only have time to go to 3 of them. So, assuming that the order in which you go to them doesn't make any difference because, I didn't say that quite right. Assuming that it doesn't mean you're backtracking or that bothers you. Okay, so most of us don't shop that way, right? We kind of do this sort of a circular pattern where we make sure that we go things in order. We're ignoring that kind of a feature because that's just our OCD heads doing that stuff. Okay, so just ignore that. All right, so let's say we only get to go to 3 of them. I'm going to make placeholders here. And the first thing I want to write down is how many different choices do I have when I go and show up at that mall? Say it like Rachel. 6. Yeah, I have 6 different stores that I'm going to sort of potentially, that's the word I want, potentially go to because I have 6 favorite stores. After I go to that store, however, how many other stores are left for me to go to? There's only 5 because I'm not going to go to the same store twice. At least that's not typically how we would shop, right? That's not the idea here. After I go to my second store, how many stores do I have left to go to? 4. And that's all I've got because I'm only going to go to 3 stores because I've run out of time. So if I take 6 times 5 times 4, what do I get? 120. That is 120. So there are 120 ways that I could go to 3 of my 6 favorite stores. Now, that does actually count the difference. Like I could go to the 3 stores in any particular order, so it would be counting the different orderings too. So if I wanted to go to Dillard's and Hobby Lobby and Kohl's, I don't think those are all in the same shopping center here, but let's pretend for a moment. Well, going to Dillard's first and going to Dillard's last among those 3 we count as different orderings. Okay, so it is counting the orderings differently like that. There's 120 ways. What if you have time to go to all 6 of them? What are you going to do? You're going to have a fun day, right? What's it going to look like mathematically?
1 times 2.
Yeah, I'm going to write it in the other order, just since I wrote the other one this way already. I have 6 options, and then I have 5 options, and then 4, and then 3, and then 2, and then 1. Eventually, there's only 1 store left to go to kind of thing. All right, so what if we multiply these guys together? There are 720 ways that we could go to all 6 of our favorite stores. All right, we're going to do one more example. I asked you to do this last time, so let's see if we can. I think I asked you to do this last time, didn't I? Yeah? Okay, so let's actually do it real quick again. You already have it written down, or maybe you've already thought of it once before. Create a real-life example of the null set in your life. So what did we have? I remember you guys had some examples, right? Somebody who didn't speak last time, what was an example you had for your null set? Do you mean to share what I have written down? This isn't what I shared last time. Apparently when I did the example, I wrote down the monkeys living in my house. That's my example. That's my null set. The monkeys living in my house. What's your example? A null set.
I put sisters.
That's right. You had the sisters, because you don't have any sisters, right? Right. So all of Caitlin's sisters. That would be a null set. Audience participation. One more, and then we'll stop the lesson. Children. The number of children you have. Okay, but I shouldn't even say number, but your children. Okay? Yeah. So this category that says my children, and it's empty right now. Very good.